Hello, this is Mustafa Abdurrahim, the first author of this paper, BIC Blind Identification Countermeasure for Malicious Thermal Sensor Attacks. In this paper, we are dealing with basically malicious thermal sensor attacks. So we are assuming that there is, some thermal sensors, and some of them, is malicious. So one of the challenges of multi-core chips nowadays is thermal challenges. So once you have, multi-cores on a single chip, then, the hotspot or the thermal hotspot will increase, with a great amount than, the single processor chip. For example, in this example here, with 16 chips, it's 110% increase in the temperature. And for that, we put, or we design efficient dynamic thermal management, DTM, which can make, a lot of, tweaks to reduce the temperature. Like, for example, dynamic voltage frequency scaling, power gating of some cores, or thermal migration. And of course, DTM depends on the thermal sensor readings to perform its tasks. So a malicious or a faulty thermal sensor is basically, a thermal sensor that report different temperatures than the actual one. So we are assuming in this paper there is an error introduced. This error can be introduced as a plus or minus, okay? And based on that, DTM will read wrong temperature. For that, hardware Trojan to be inserted, there are, some scenarios, for example, like using third-party thermal sensor, like, for example, the thermal sensor resonators, MRRs, which are very accurate, thermal sensors, but usually depend on different technology. So, in these cases, the main designer may opt to use, other technology in other companies, to implement the thermal sensor. Also, another scenario is using a third-party processing core, or or a processor basically that come with its own thermal sensors. For example, the foreign designer, knows exactly where the hotspot came from in the processor core, so she should put, the thermal sensor close enough to that hotspot. Another scenario for reporting, incorrect temperature is having a faulty sensor, which is also a very big possibility. This may happen due to fabrication faults or aging effects, and also because, thermal sensors are very susceptible to noise and the process variations. The impact of a malicious reporting or incorrect temperature, is basically twofold here. So in either case, if you increase, if you report more than the actual value or less than the actual value, in both cases there will be negative effects. If you report more than the actual values, they might think that the chip is overheating mistakenly, of course. So it might activate some unnecessary thermal management, protocol like, frequency throttling, which will degrade the performance, unnecessary, of course. And if you report less temperature, that's also dangerous, because the DTM will think, the chip is safe. Also, as you increase the temperature, this will reduce the lifetime of the chip, and also will induce, higher leakage power. And there is, a famous rule of thumb that, a 10 degrees increase in the average temperature, operating temperature of the chip will reduce the lifetime by half. So here is our attack model. So the hardware Trojan that is inserted into the chip has the following characteristics. It has a random back-off time between attack triggers in order to decrease, the probability of discovering it. The first attack, and this is a very important assumption, the first attack will take place after a long time of the first usage, for example, weeks, so that, during design time, it might be difficult for the it will not trigger, and the design engineer wouldn't detect the attack. Also, the triggers the attack when the steady state temperature is reached, and stop if the temperature reduced or start to decline from the steady state. Because at the steady state, that's the highest temperature possible for that workload. So, it's usually expected that at the steady state we have high temperature. And similar to other researchers, we consider the existence of a single hardware Trojan in the system, so that it's a light hardware Trojan implementation, so it will be hard to be detected as well. Our attack countermeasure BICs, or BIC, depend on a famous algorithm called Blind Identification, or BBI for short. So BBI is a famous, algorithm that, construct basically the thermal characteristic equation of any system. So any system, any processor for any chip basically can be characterized using this equation here. T of K, T of the temperature at time K equal to some constant A dependent. This constant A matrix is a constant matrix dependent on the system itself, multiplied by T at a previous temperature, Tk minus 1, a previous time, plus another constant B, which is also dependent on the characteristics of the system, multiplied by the power at the time K. BBI basically is an algorithm that use basically the total power and the thermal sensor reading of each core to construct A and B. And in the way, it will construct another matrix called the thermal resistance matrix, which is very important matrix that is dependent on both A and B, that is also constant for the system. Usually our system, or our chip has, a thermal sensor per core, maybe even more, but one power sensor, because power sensors are big, and it's complicated. It complicates the design of the chip. So usually we have just one power sensor that measures the total power of the cores combined, but for each core we have a separate thermal sensor, and that's enough information for BBI to construct A, B, and R. Our main idea, or the big main idea here, is to estimate R, which is again a system dependent. It doesn't depend on the workload or the temperature or the power, and we can estimate the correct one, which we can call our golden of the system. Then we're gonna, during chip testing before production, and then re-estimate R during runtime, which we will call our runtime. And basically, if there is an attack, if there is a hardware Trojan, our runtime will be not equal to our golden, and that will be our key to determine or detect basically the attack. Okay, so BIC has main 4 phases or stages. The first stage is, our golden construction, in which, or phase 1. This phase 1 happens offline before the production of the chip to users. And since, as we said, in that case, the attack will not be triggered, so the resistance the matrix that we will estimate will be correct. Then the second and the third phase happens during runtime, periodically, online, in field. So in that case, we're gonna re-estimate R, and basically if R golden doesn't equal to R runtime, then we have an attack. We will detect the attack, and then we need to identify the attacker. And why we need to identify the attacker or the malicious thermal sensor? So that we can run, the fourth phase, which is basically to estimate, try to estimate, the temperature that should be predicted by, this malicious sensor. Here is the first phase, our golden construction. And we said that, in our attack model, the the attack is assumed will not be triggered during or after very long time to avoid being detected during the testing of the chip in the factory or in the the design company. But even if it's triggered, there are also other ways to measure the temperature offline, for example, using a thermal camera, high resolution thermal camera. So we can avoid completely the use of the thermal sensors. And in either we did that or this, we were gonna construct our golden. Phase 2, which happens in field during runtime of the chip. So this this attack detection phase runs as follows. So we periodically recomputes R, which we're gonna call R runtime here, based on the sensor measurements, of course. And again, if R runtime doesn't equal to R golden, then we have a malicious sensor. So we need some inequality criteria here. So basically, for any core, what we're gonna do is we're gonna compare each corresponding elements in R runtime and R golden, and we're gonna put like a tolerance zeta here. And if the difference exceeds zeta, then we're gonna consider this as not equality or not equal, and we detected the attack. If we detect the attack, we need to identify which thermal sensor is the malicious one. And here we're gonna do what's called blocking or sub-estimation of R. So if, for example, you have 3-core system, so a processor that has 3 cores, then R will be a 3x3 matrix like this one. Okay, but actually let's assume that one of the cores, for example, is defect. So it will not work. So we don't need to run anything on that core. And in that case, our processor will be just 2 cores. For example, we have a faulty core. So in that case, we're gonna have only 2 cores. And in that case, we just need 2x2 matrix. And one of the good thing about estimating R is that you can deduce the submatrices out of the main matrix R here. Okay, and you can even estimate them independently without having R in the first place. So for example, if core 1 is idle, I mean there is nothing, there is no workload on core 1, it's offline, for example, and only core 2 and core 3 are working, then if you run thermal traces and collect the power, BBI can estimate the submatrix here, which I'm gonna call here R sub 1. And if another example, if core or core 3 is idle, then you're gonna have only core 1 and core 2, and you're gonna estimate the orange submatrix here, submatrix 3. So now the idea to detect the malicious sensor is that the cores that we exclude, we're gonna exclude its thermal sensing reading. So if it's thermal sensor is the malicious one, then we excluded the malicious estimate, the malicious reporting. So the R submatrix that we're gonna estimate will be correct one. So basically, for example, if thermal sensor 1 is the malicious one, since in estimating R sub 1 we exclude core 1 and it's a malicious sensor, then we're expecting that R runtime sub 1 will be equal to R golden sub 1, while R runtime sub 2 and R golden sub 2 doesn't equal to each other, and the same for sub 3. And that way we can estimate or know basically the attacker. The third the fourth phase of BIC is a measurement estimation. Since we excluded some of the one sensor, for example, then DTM needs to continue its operation. So we need to re-estimate its temperature. So remember that in that case here, after detecting the thermal sensor, now one of the temperatures are completely incorrect, so it can be considered unknown. Like for example, here, if we assume that core 1 has the malicious sensor, then T1 is unknown here. We know that T equal to R multiplied by B. This is, the steady state, equation is, system equation. R is our golden, we know it. And B, remember, the power is also unknown because we don't know B1, B2, B3, B4, but we know the total power, which is the summation of B1, B2, B3, B4. So what we're gonna do is we have two steps. Step one, we're gonna estimate B first. So we're gonna solve this system of equation. We're gonna exclude T1 and the first, row here. And we know we're gonna minimize this system such that each one of the B's here is greater than 0, and the first norm of B, which is basically the summation or the total power, equal to B total, which we can measure and we know. Then we can find T1, which is our unknown here, using that simple vector multiplication or matrix multiplication. Here is our evaluation setup. We tried the 3 different layouts: a 2x2 core or 4 cores processor, a heterogeneous processor application for smartphones, and a 16 core processor. Here is our setup. Basically, we use the hotspot thermal tool. We provided the layout information and the power traces. Then hotspot will give us, the temperature traces for each core. Then we introduce manually, the delta T error, and then we apply our BIC, phase detection, then identification, and finally the estimation, which of course will correct delta T plus T1 into T1 again. Here is our results. So we see here that the error, or the failure means the failure to detect the attack or identify the attacker. Each one is considered a complete failure. So here we see that the failures increase as we decrease delta T error. Okay, so if delta T error decreased, then you have more possibilities that BIC will fail. And also if and also it plateau, or the failures will plateau at the number of cores, and it will be proportional to zeta. As zeta increase, then there is a higher probability that we're gonna exceed the main difference between our runtime and our golden. Here is another insight, which is showing the change or the failures, the percentage failures with delta T error. As we see here, most of the time we have zero failure, and the failures happens between -5 and 5. So basically the BIC achieves 100% success if delta T error is greater than or equal to 6 Celsius. And again, as a reminder here, we are expecting that the errors will be more than or equal to 10 Celsius to achieve higher impact, or higher negative impact, of course, for the attacker side. Here is some case study, for example, from 2x2, just to show you that really, introducing error will change the matrices. So this is, for example, our golden. Here, thermal sensor 1 has the error. So as you see here, for example, our golden 1.1, this value is 0.7. Here it's 1.1. So we have here a difference of 0.4, and the zeta here was 0.2. As we said, zeta is the tolerance is a design parameter. Here is the submatrices. Here is we have 4 core systems, so we have 4 submatrices. Since malicious sensor 1 is the malicious one, So this is R sub 1, this is R sub 2, sub 3, and sub 4. And if we apply this equation here, in which we subtract each corresponding values in the submatrices, we're gonna find that the minimum happens at R sub 1, because when we estimate R sub 1, we exclude the malicious sensor. Here is the measurement estimation accuracy, and the accuracy is really high. So the maximum accuracy, the maximum error here happen equal to just 0.18. And the reason is that BBI preserves the characteristics of R matrix, because, like, for example, symmetry, so that it estimates R very accurately, and that's the needed parameter to estimate the temperature accurately enough. Now for the performance overhead, so phase 1 has no performance overhead, because to estimate R golden we do that offline. But phase 2 and 3, which is the detection and the identification of the attacker, happens online. But here we say that, or we propose to activate these phases on a relaxed manner, since we need to run it until we detect the attacker, so we can have a relaxed triggering. For example, we can run these phases before a user reboot, or during sleep or inactive periods of the device or the processor, or as, for example, as a security update. So the user will accept the running of such phases. So again, phase 2 and 3 has a negligible overhead, but maybe phase 4 has some overhead. So for that, we run phase 4 with a rate of 250 milliseconds, which is enough rate, because we are detecting or estimating the steady state temperature, and steady state temperature takes tens of milliseconds to be reached, actually seconds sometimes on server processor, for example. And we run our algorithm on Android HDK kit, which has a Qualcomm Snapdragon processor. Here is the result. As we see here, they are very close. So the scores of Geekbench 4.3.1 are very close before and after running our phase 4, and the maximum percentage difference doesn't exceed 0.7%. Here is our main conclusion. BIC achieves 100% detection if for any temperature error greater than or equal to 6 Celsius. The accuracy of temperature estimation is really very high, just below 0.18 Celsius error, and the performance overhead is really negligible. Thank you very much for watching, and I'm ready for the questions and answers. Bye-bye.